In this chapter, we'll talk about lipids, their types, and their function. So in simple terms, lipids are molecules that contain hydrocarbons, and they make up the building blocks of structure and function of living cells. Examples of lipids include fats, oils, waxes, vitamins, certain vitamins, like for example, vitamin A, vitamin D, vitamin K, all of those are examples of lipids. Hormones as well, and most of cell membrane that is not made up of protein. Now, lipids are water insoluble. And they are soluble in non-polar solvents. Non-polar solvents, like any solvent that doesn't hydrogen bond with water or does not dissolve in water, we call it a non-polar solvent. Fats are part of cell membranes, and they do help control what goes in and out of the cell. Their major role is in moving, in storing energy, absorbing vitamins, and making hormones. So for example, if I have this question over here, picking the right solvent to dissolve a lipid. Lipid, think of lipid as an oil. This means that it is water insoluble. Why? Because it is a long hydrocarbon chain. And we know that any organic compound that is made up of more than 5 carbons, its water solubility is going to decrease. Lipid has a lot of carbons in its chain, so there is no way that it is water soluble. So it has to dissolve in a non-polar solvent. So for the first one, I do have a tertiary butyl alcohol compared. So I do have a tertiary butyl alcohol in there. So that is my alcohol. As long as I have an alcohol, this is 4 carbons in there. This is water soluble. So this alcohol is going to be water soluble. And I'm going to call this a polar solvent versus the ether, which is a non-polar solvent. Why it is a non-polar solvent? It is a non-polar solvent because it does not have a hydrogen connected to the oxygen. So it is not a hydrogen donor. So this one is considered to be an organic solvent compared to a polar solvent in there. This one mixes with water. This one, the diethyl ether, has 2 options. It can mix with water because it can hydrogen bond with water, but at the same time, it is an organic solvent. So it plays a double role in this case. So that is the best solvent in order to dissolve the lipid. So over here, the diethyl ether. So this one is my diethyl ether. So the diethyl ether is a good solvent for dissolving lipids. So all what you need to look for is a non-polar solvent. This is what you need to look for. So between water and this is 6, 7, 8 carbons, it is octane. So between water and octane, of course, octane is going to be my non-polar solvent. So octane is a good solvent in order to dissolve a lipid. Water is a polar solvent and it is a bad solvent. It cannot dissolve lipids because lipids, after all, these are oil and water cannot dissolve oil. So for the classification of lipids in there, this table you can have in the exam, and I'll include it in the exam table sheet. Okay, so lipids are classified into saponifiable lipids and non-saponifiable lipids. So by definition, a saponifiable lipid is a lipid that contains ester, and the ester can undergo basic hydrolysis. Okay, so these lipids, they contain an ester group that undergoes basic hydrolysis. Okay, So this is what saponifiable is. Non-saponifiable lipids, these are lipids that do not contain an ester. So these are lipids that do not contain an ester, and they cannot be hydrolyzed. Okay, they cannot be hydrolyzed in this case. Saponifiable lipids are divided into two types of lipids: a simple lipid and a complex lipid. Now, simple lipids, these contain one or more fatty acids and an alcohol. This is what a simple lipid is. So a simple lipid, these contain one or more fatty acid and an alcohol, and an alcohol molecule. In this case, the fatty acid and the alcohol will react with each other, and you will make a simple lipid. Two types of simple lipids: we have waxes and we have triglycerides. Okay, the complex lipids, on the other hand, these are ester containing lipids. So complex lipids, these are ester containing lipids with more than two types of components. So with more than two types of components in there, you do have an alcohol, fatty acid, and other components. So an alcohol, so you have an alcohol, you have a fatty acid in there. So the alcohol and the fatty acid is a must, but in addition to this is why we call them complex, because with simple, you have a fatty acid and the alcohol. But with complex, you do have the fatty acid and the alcohol and then additional other components, plus other components in there. Okay, so that is for the complex lipids. The complex lipids are classified into phosphoglycerides and sphingolipids. And then for the non-saponifiable lipids, there are two types: the steroids and the prostaglandins in there. Let's start by defining the building block of the lipid, which is the fatty acid. So these are building blocks of many lipids. These are long chains of carboxylic acids. And the long chains of carboxylic acids, the value of the carbons in there, it's between C10 and C20, okay? So it's between 10 carbons and 20 carbons in there. They do have a long nonpolar tail, which is responsible for the fatty and the oily characteristic in there. So this is the structure of a fatty acid. And that fatty acid has a hydrophobic tail. That hydrophobic tail is a long carbon chain that heats water. So this is a water repellent. This is the nonpolar part of the fatty acid. And then you have the polar head. This is the polar part. We call it the hydrophilic head. This is attracted by water. So this part is water soluble. The tail is water non-soluble. So in order to simply represent a fatty acid, after all, this is an acid. So if it is an acid, then it has to have a carboxylic acid functional group at the end. And that we call it the polar head, the head of the fatty acid in there. Okay. So what happens to fatty acids whenever we place them in water? In water, these fatty acids, because you do have that hydrophobic tail that is water repellent, they're going to arrange themselves in a circular form. That circular form, we call it it's a spherical cluster, which we call it micelles. And these micelles in there, they do have a very important job in transporting insoluble lipids in the blood, because lipids are they are water insoluble. So this is how they are transported through blood and thereby forming spherical clusters or micelles. So we said that fatty acids, they always have an even number of carbons. They do not have an odd number of carbons. Pay attention to that. It's a long carbon chain between C10 and C20. And within their carbon chain, you can either have double bonds in there, so the fatty acid will be unsaturated. So whenever you have a double bond, the fatty acid will be unsaturated. We call it an unsaturated fatty acid. This means that the double bonds are present. And there is an option also for fatty acids to have no double bonds in them. So if they don't, then the fatty acid will be called saturated fatty acid. Now, if the fatty acid has a double bond, then the groups around the double bond will prefer to arrange themselves in a cis configuration in there. So this is how it's going to look like. You are going to see that the groups are going to face each other. You will have hydrogens in there, and you will have a cis configuration. For saturated fatty acids have no double bond in them. So if they don't have a double bond, these will assume a straight structure. Okay, they will assume a straight structure. For fatty acids that have double bonds in them, the double bond causes the fatty acid to tilt, okay, or to bend. We call it kinking of the carbons in there, because the groups are going to be cis with respect to each other in there. So fatty acids that have carbon double bond carbon bonds, these, if I want to put them next to each other, because you notice here, the more double bonds, the more kinking I'm going to end up having within the fatty acid structure in there. So if I have multiple fatty acids that have a lot of double bonds in there, and if I want to pack them together, they are not going to pack closely together as the saturated one. The saturated one is a straight one. It's easy to pack those together, so there will be a lot of intermolecular attraction between them. But for these fatty acids that have double bonds, when I want to pack them together, they're going to be far away from each other. So this will lead to a decreased intermolecular interactions in there within the structure. So this is why unsaturated fatty acids, they do have a low melting point. So let's put this over here. So this is why unsaturated fatty acids, they are liquid at room temperature, and they have a lower melting point. These are liquids at room temperature and have a lower melting point. Lower melting point because the intermolecular interactions in there, it's very low, because the molecules, when you pack them next to each other, they are actually far away from each other. They don't interact. So if they don't interact, that is going to decrease the melting point. And decreasing the melting point will make unsaturated fatty acids to be liquids at room temperature in there. So the rule says that as I increase the number of double bonds in the fatty acid structure, as the melting point is going to decrease. So more carbon double bond carbon, more alkenes in there in the fatty acid structure, the melting point will decrease. This is why here I do have three structures of fatty acids. I have stearic acid. Stearic acid is a saturated fatty acid in there. So see how the melting point, this is 71 degrees, compared to the melting point of oleic acid has 1 C double bond C, and linoleic acid here, it does have 2 C double bond Cs. As I increase the number of the double bonds, the melting point over there is going to decrease. So that is going to be the lowest melting point compared to the oleic acid and the stearic acid there. Now, for fatty acids that are saturated, so these two are unsaturated. Fatty acids that are saturated, these are solids at room temperature. They are solids because they can pack easily together. And when they pack together, the intermolecular forces between the fatty acid molecules is going to increase. Okay, so that will cause them to have a higher melting point. So let's have an example there. Indicate whether each of the following fatty acids, again. Now, all of these fatty acids in there is a table with all of the fatty acids and their names. You don't have to memorize any of those. So if I ask you about these fatty acids, all what you need to do is just go to that table, pick up the fatty acid in question, and work with it. So indicate whether each of the following fatty acids is saturated or unsaturated. So in order to answer this, the first thing that you would need to do is simply look at the fatty acid and see if it has a double bond or not. If it doesn't have a double bond, like this one there, then it's going to be saturated. And if it has a double bond, then it's going to be unsaturated. And this one is going to be unsaturated as well. Okay? Then what I need to do is I need to count how many double bonds I have. It says that indicate whether each one of those is going to be solid or liquid at room temperature. Now we know that for saturated fatty acids, these are going to be solids at room temperature. Okay, unsaturated is going to be a liquid. And this one is going to be a liquid as well. So the presence of the double bond is going to decrease the melting point, guys. Decrease the melting point in there and causes the fatty acid to be liquid. I'm going to add this additional question in there. Which one has the lowest melting point? So lowest melting point in there. So which one has the lowest melting point? Add or count your number of double bonds. So here I do have 2 double bonds, okay? And here, see, I have 3 double bonds because the whole thing is to the 3. So I have 3 double bonds in there. So that is going to be 3 double bonds. Remember that the more the double bond, the lowest is the melting point. So as the number of double bonds increase, as the melting point is going to decrease. So this structure here is going to have the lowest melting point, and this structure is going to have the highest melting point.